All right. Thanks for the intro, Phil, and thanks, Dan, for hosting us today. Hey, everyone. I'm Sujay. As Phil had mentioned, I'm the co-founder and chief scientist of a startup called Convex. And today we'll be talking about full text search, and specifically, elegant full text search. OK, so the kind of setting we have today is that we're working on Convex, and Convex is a backend as a service. So it's a combination of a database. So it's like an OLTP database that stores your application data. It runs your functions, so it runs code. It can run background jobs. It can have your APIs. It's kind of like the answer to the thought experiment of like, if you wanted to have a full stack developer be able to build an app end to end without ever having to open the AWS console, like what primitives would they need? Like, what are like the core ingredients for like the kind of distributed operating system that's needed to build stuff like that? And so about like, I think a year and a half ago, we had a bunch of users who are building apps on Convex. I think I used like a Notion clone as a running example. And people kept on asking us like, hey, I would like to add full text search to my product. And up until that point, we had kind of just told folks like, you have your database in Convex, much like you might have your database in MySQL or Postgres. Just use replication and replicate it out to another system like Elasticsearch and do your search there. But people kept on saying like, hey, that's too much of a pain. Like, can you just do it in line? And to compare to a system like Postgres, Postgres, for example, has full text search built in. And our customers would tell us that they would get started building their apps on Postgres, and after a while they would want to add search and just use the built-in functionality on Postgres for a really long time, for like a surprisingly long time, until they decided they needed to move off to something that had more flexibility or was more specialized to that particular domain. So when we decided we wanted to add text search to Convex, a few of us just started reading a bunch about what text search is, because it's kind of actually a pretty ambiguous question, right? Like if you imagine that, hopefully this is big enough for folks to kind of see the big idea. If you have like a document open in Notion and you do applique, and then you type in something like New York City systems text search, and you get a bunch of results, and these results are in some order, like what is actually happening under the hood? And at least I'll speak for myself and for some of the folks I worked with, it was just entirely like an impenetrable black box, right? Like I have no idea how this string goes in and these results go out. So by digging into it, we found that there's actually a really beautiful, elegant kind of algorithmic core to full text search. And that's what we'll be talking about today. Before we go into it, one thing that I definitely want to call out here is that we'll be focusing on text search in the context of what I like to call application search. So this is something like Notion, or you can imagine for like an Asana. I think like Slack is another good example. These are systems where there's an underlying like maybe relational data model, and the user wants to, it's very structured, and users want to search within it. I'm not going to talk about like something like Google, where there's like a huge library of content that's like mostly immutable, and users want to search through that. And I'm not going to talk about stuff like log search, which the second talk might go into, where there's like a very, very large scale, low user value per gigabyte data set, and where queries need to be performed against that. So to kind of reiterate here, like I think one of the interesting parts of the type of search we'll be talking about today is that it has very high value per user gigabyte. Like developers are willing to pay to store this type of data on SSDs, and they want it to have like high write throughput. They want it to be very fresh. They want queries to be answered quickly, and they're not going to scale past maybe like a few terabytes. I mean, unless they're enormously successful. Okay. The other thing I want to call out is, given how hot it is these days, I'm not going to talk about like semantic search. I'm not going to talk about with embeddings and doing approximate nearest neighbors. Convex actually also has that, and could talk about that later. But this is like old school, like inverted index keyword search, like the stuff that's been, the bedrock of information retrieval for a long time. Okay, So when we started digging into this, and we're trying to see like what's going on under the hood for full text search, there's just way too much. I just thought, I looked at, we're digging into how a system like Elasticsearch works, and there's like, YQL, ESQL, EQL, there's like UniDecode, learning to rank, there's all of this stuff. And this is part of, I think, what leads to search feeling like a really impenetrable black box. And especially as like a systems engineer, when we're working on a system like this, and I always want to know, like, what are the resources being consumed? Like, what is actually being stored on disk? Where is throughput being limited? Is it being limited by I/O, or is there compute? What is actually causing query latency? How are queries being planned? And by looking at this whole mess of stuff, I think all of us were kind of like, we don't really know how we're going to implement this in Convex, and especially for the decision of whether to build or buy. Do we build a search system in-house that uses libraries, say like Lucene or Tantivy is the one we ended up picking, which I'll shout out Tantivy. It's actually a great open source search implementation. Or do we just deploy Elasticsearch internally and then, or maybe OpenSearch or whatever, and like kind of just resell that to our customers? So the kind of core premise for this talk is that despite there being all of this stuff that is there when you search for blog posts on full text search and you look at documentation, there's actually a very beautiful, elegant algorithmic core on it that it was quite unfamiliar to me as like coming from the databases background and thinking about B trees and query plants and stuff like that. And there's only really two main data structures that are involved, and they're combined in a pretty clever way. So once we dug into all of this and we kind of had this perspective for how search works, and kind of like pulling that thread led to a lot of design decisions being made for us when we implemented search in Convex and let us tailor it to specifically the requirements of our workload. Okay, so we'll walk through a search from the very beginning, and we'll do it in this very in this opinionated way, coming from like the way that I think we should think about search, and then we'll sweep a lot of details under the rug. And then at the end, we can reintroduce some of them if we have time. Also, actually, Phil, let me know when. I didn't notice when we started. OK, so the first kind of part of executing a search query. So say like I went into my Notion app and I typed for NYC systems, and this was my query string. The first part of executing a search query is called tokenization. And pretty much every search system we encountered falls. Pretty much every search system we encountered has some form of tokenization, where it takes an input string, like NYC systems, and it breaks it up into words. So in this case, we're just splitting on white space. So there's NYC and there's systems. As you can imagine, there are very, very sophisticated ways to do this. I think this is where a lot of the boxes come from on that previous slide. You can imagine that in different languages, you may want to split things differently, or for different algorithms, like for code search, where people want more exact search, they do different things. But for now, let's just assume that it's very simple, and we just split on white space. So when I'm searching for New York City systems, I split it into two words, NYC and systems. OK, now this was the thing that was actually very surprising to me. And maybe this is like basic for anyone who's actually worked in this like space before, but from coming from the outside, one thing that was really surprising to me is that whenever, in pretty much all the systems we encountered, when someone searches for NYC systems, that gets churned into a very simple like Boolean query. It says like, please just find me any document inside the data set that contains the word NYC or contains the word systems. So it's take the union of the set of all documents that contain NYC, the set of all documents that contain systems, take their union, and then maybe intersect them with, like, since this is Notion and I should only search for my own documents or documents I have access to, do a set intersection of that set of documents with the set for the ones that I have access to or the ones that I own. So I remember this like kind of being pretty surprising to me, because there's a lot of ways that you can have a document contain NYC and systems. They might be in totally the wrong order. It might have duplicates of either one. But a lot of systems map an input query like this to something that's very simple. And we'll see later how the results become smarter. But at the core, It's just like these very simple set operations. Okay, so the next step that shows up in a lot of systems is called ranking. And we mentioned how, like, at this step in the very first step, we take the union of all documents that contain New York City and all the documents that contain systems and intersect it with the ones I have. And at the end of the day, we only want to show a bounded number of them to the user. And we want to show the most relevant ones. We don't want to show, if a document just happens to only contain NYC, we would much prefer to show a document that contains both of the words. And this is a whole nother topic that we're not going to get into, just to sweep under the rug, because it doesn't actually really show up that much in the data structures. But let's just assume that there's a really easy way for us to compute the relevance of a particular document in our query set, and then we just sort by that relevance and take the top 1,000 results. Or if we're really fancy, maybe we have a heap that maintains the top 1,000, and we iterate through this result set and keep only the top results. There's actually even another thing we're going to skip. Most of the systems that we encountered do some form of re-ranking. So when we took the top 1,000 results, this was potentially with a very cheap notion of relevance that just counts, say, like the number of matches, like how many of the words in the query show up in the result. But then that's like very simple. And what a lot of systems do is they'll take the top 1,000 results, compute some more expensive metric. So like this might be one where they load a row from the database and use that as some signal on like whether it's a good fit or not. And then compute 1,000 of those more expensive metrics and then take the top 100. And then they may even resort again with an even fancier one that uses some fancy pants machine learning algorithm that we're definitely not going to get into today, and take the top 10, and then those 10 are what show up in the UI. Like I was saying before, we're going to skip all this. We're just going to only go up to this point because that's, in my mind, the kind of like algorithmically interesting part. And all of the rest of the part is just like computing scores and resorting. Okay. Cool. So one of the first data structures we have is a sorted integer set. I think this is like one of the really cool parts of doing full text search. And the core idea, I think one of the big themes for systems that do text search is that static immutable data structures are awesome. That you can do so much more when you know that your data is immutable. And we will eventually, maybe if we have time, we can talk about how we make data structures that use immutable pieces support updates. But for now, let's just assume that our data set is static. So one of the first things that we can do when we have an immutable data structure is, this is maybe a little bit too small, but like let's say that my data set has 3 documents. I have one that's owned by me, and then the contents have like this talk. I have a second one that is owned by James, and then he's saying something about convex. And then I have a third one that's owned by Jamie, and he's saying something about caching. Since we know that this set of documents is static, we can just choose some ordering of them. And instead of having to use some complicated primary key or something to identify them, we can just assign small integers to each one. So I'll assign 0 to the first one that's owned by me, 1 to the one that's owned by James, and 2 to the one that's owned by Jamie. So this gives us very compact, small identifiers for each document in a way that fundamentally kind of relies on the data set being static. There is like work that's done for assigning small integers to dynamic data sets, but that's like a hugely more complicated problem. Cool. So then the next important part, and this is I think one of the key ideas for text search, is that now that we have a small integer for each document, we'll take every word that exists within our data set. So there's 5 words that exist within these snippets. And we will store a sorted integer set of which documents the word appears in. So like the word convex appears only in document 1. Caching only appears in document 2. The word is here is in both. It's in documents 1 and 2. So note here that we're storing it in monotonically increasing order. And then for the other 2 words, they only appear in the first one. So notationally, this is like one way of thinking about it, where you have these just arrays in memory that store these small integers, and then they're stored in ascending order. As a better notation, I like kind of thinking about these almost as like kind of number lines. So there's the document ID space. So these small integers are called document IDs in a lot of systems. They're going from left to right. And then when we have a word, we put a dot for every document that that word appears in. So we've changed these like arrays of integers into these like timelines. And then the cool thing we can do with sorted integer sets is that we can efficiently, in a streaming way, compute both their union and their intersection. And so if we go back to our original query where the kind of inner part of it said that we wanted to find all of the documents that contained NYC and all of the documents, or sorry, a document that contained the word systems, when we represent these sets of documents as these sorted integer lists, we have these two arrows where hopefully this is not too small to see. And we want to efficiently compute the union of these two sets. And computing this union is like, kind of just doing like a merge of two sorted lists, right? I can initialize this blue pointer, which says like the current position in the list, to the first one. And let's see. I can then see of the two pointers which one is furthest to the left, emit that, and then advance that pointer to the next element, emit that, and then advance the one that I emitted. Now I know that the second set is before the first one, so I can emit that. And then when I advance it to the next element, I notice that these two are lined up, so I only emit that document once. So another kind of good property here is that we're also emitting these document IDs in sorted order themselves, which will then help us combine it with other parts of our query. Cool. The other algorithm, which I think is quite nice, it's very simple, but it's like it works really well in these systems, is for computing set intersection. So going back to our previous example, we took the union of these two sets, and then we created the union here, which I'll have as the first line, and I've kind of pre-materialized it. And then say I have another set which represents all of the documents that have user equals Sujay. And so I have that as my second one here. And when we are computing the intersection of these two sets, we want to find all of the vertical lines that hit dots. We want to find dots that are present in both of the sets. So right now when we initialize our pointers at the beginning, they don't line up. And we're trying to get these pointers to line up. So we know then that this pointer on the left and also its subsequent element can never be in the intersection because the smallest element in the second list is right here. So we can do a seek where we use binary search or however we implement it to jump this blue pointer, the first pointer, to the first element that is greater than or equal to the blue pointer on the second set. So we do that, and we notice it still doesn't match. And then we do a binary search again, and we move this pointer, the second pointer, to the first element, which is greater than or equal to the first pointer. And now we have a match, and we emit that. So we keep on doing this, and the pointers kind of zigzag back and forth, and they never quite line up. And then after we advance this pointer, we know that we've run off the end, and once we've exhausted a set, we know that there's no further results. So one of the kind of cool parts with this algorithm is that it scales in the size of the smallest set, right? We did at worst a binary search per element in this set, and this other set could be really, really large. Like if you imagine that this, say we had the word the in our query, and the appears in 90% of our document set, having a selective filter here lets us prevent doing a lot of I/O. Cool. So if we put it all together, and I realize actually this might be a little too involved, but it ends up kind of composing really well, where we have this intersection that's on the outside, and we have the union that's on the inside, and these pointers can all kind of jump forward and back, just forwards, and they find matches, and as we iterate over the intersection, we move these pointers for the union forward. So I can go into this in more detail, but we're probably low on time. Anyways. Cool. So the other data structure is actually very simple, and it's like the only real other data structure, I think, for the work that we need to do. And it's the term dictionary. And the term dictionary is just a key value from the unique terms in our data set to the integer sets that we were iterating over. So I kind of swept this under the rug when I said, like, we're executing this query and we managed to get these integer sets. But when we're executing the query, we do need to like be able to find them on disk. And that's done by using a term dictionary, which just says, like, for the word caching, here is how you find its set. Cool. So taking this like very opinionated view of full text search and kind of synthesizing it together is really just a few steps. You take an input query, you tokenize it, and you turn it into multiple words. For every word, you use the term dictionary to look up the integer set for each one of those words. You do some traversal of those integer sets, maybe doing intersections or unions to get the final result. And then you sort the final result by your relevance score and take the top results. And so that's the ranking. And that's pretty much it for a high level. I think there is so much more to how this stuff actually works under the hood, what data structures it's using on disk, how like query planning works and everything. And I have some, I don't know if the slides will be shared out, but I have some pointers to like more stuff on how it works under the hood. But like I feel like all of these kind of like are incremental sophistications on that underlying model. And by accruing a lot of those incremental sophistications, we can get to a system that has really high performance and scales well. So, and that's it. Thank you. Do we have time for questions?
Yeah, and just repeat them into the mic for the.
Okay, yeah, sure. Yeah.
I feel like a lot of full text search systems also will account for the fact that you're, like if I type THW or something, or
Yeah.
THQ accidentally,
Yeah.
how does that sort of tie into this exact matches in the question?
Yeah, totally. So the question was, like, a lot of full text searches will support some form of inexact matching, like either some edit distance or like prefix search. Is that getting the question right? And how is that accommodated? Yeah, that's a really good question. And so that is why, like, this second slide, this like second data structure slide on the term dictionary is very, very sparse. And the reason why I think this term dictionary deserves to be one of two data structures is that most systems in practice will use something that lets, that is amenable to doing this like typo tolerant search. So like the term dictionary here isn't just a simple key value of word to posting list or to integer set. It will be often like a try. And then, so that's the, one of the posts I linked here, this like index 1.6 billion keys with automata and Rust. That is like a really amazing post by Burnt Sushi, who implemented this crate called FST that implements an on-disk data structure for doing, if we're implementing a try, a static try. And so the kind of core idea is like if we went back to like searching this data set, if I search for the word like IT, like it, and that doesn't exist inside, that word doesn't exist in my data set, but if these 5 strings are stored in a try, then I can say like, create the like Levenstein automata that it like represents edit distance, say up to 2. Like it allows like one edit or an insertion or deletion, and intersect that automata with the try, and then that will be able to find the word is. And the kind of interesting thing, I think, is that the cardinality of the set of words in the document set, especially if it's natural language, is much smaller than the total cardinality of all of the documents, right? So this try, despite, you know, like Burnt Sushi has a post on doing 1.6 billion words, and from what I understand, like indexing systems in practice often have to handle things like URLs or like, it's not always just pure English words. But this problem is entirely solved at this stage, where we first take our query words, use the automata to find some set of integers, of some set of integer sets that it will then put down into the union and intersection algorithms. And the kind of fuzzy matching is done by that point. Yeah?
Where does inverted index fit into all that?
Yeah, so the question is, where does inverted index fit into all of this? Yeah, I've actually avoided using that term, but this is like this process of storing like the words mapping to documents, that is like the inverted index. And so the reason why it's called an inverted index is normally you would think of storing the document to the list of words. And here we're inverting it by storing a word to the list of documents. And other, I didn't show it here, but like systems will often, in addition to storing that like is, or say talk is in document 0, it might also store the positions of like it's in document 0, but also at positions like 4, 7, and 8. And then with all of that data, now it's invertible. Now we can go back and recreate the original data set.
Can you go back to the union upper line slide?
Yeah, so going back to the union slide.
Yeah, so you mentioned that you can do this in a streaming fashion, which is nice. Can you parallelize it? You only used 2-word example, but if there was like 5 or 6, do you have to just do them serially, or can you emit them? The same with the intersection as well.
Yeah, so the question is for the union and intersection algorithms, can we do them in parallel, or do we have to do them in serial? In practice, I think most systems will utilize like more hardware by splitting up the document set into many partitions and then executing queries in parallel across the partitions. And then the algorithms for merging these sets, I mean, and yeah, there could be many sets that we're taking the union of and many sets we're taking the intersection of. To the best of my knowledge, I mean, there's like some SIMD stuff for being able to like really blast through them quickly. I don't know if folks generally multi-thread this. I think the kind of like parallelization is done at a much coarser level. Yeah. Question back.
Like using something that works over a bit vector, like rank and select, the operation that requires binary search could be made faster. Is it like the reason you didn't do that is because these are too sparse? Is that?
Yeah, so the question is like there are succinct data structures like rank and select for bit vectors that support really efficient like predecessor and successor queries, right? So being able to say like when I'm jumping, a better example would be for the intersection. Like when I'm jumping forward to say like please jump me to the point past this, there's structures that implement that really efficiently. It's a good question. To the best of my knowledge, like I think a lot of these systems are very disk-oriented. So like the kind of optimizations that folks are doing are to like break these up into blocks and then to store some summary structures like on a per block level that's like kept efficient and kept like so it doesn't have to do a seek. And then like within a block are folks doing like rank and select type things. I haven't seen it. I mean, it definitely is like very topical. I think a lot of it is more on the kind of like integer compression side. So it's like stuff like bit packing and trying to get, which is similar in spirit, but is like trying to get it so decompression speeds are really fast. Yeah.
Are there typically like optimizations that use natural language, like in the sense that the frequency distribution of words isn't uniform? Like the word appears a lot, maybe like the word tokenization appears very rarely. Like are there ways to take advantage of that?
Yeah, so the question is like, are there optimizations that use like different observations about natural language? So like, for example, knowing that the word the is very frequent and doesn't have that much like semantic meaning attached to it within the system. Yeah, absolutely. And like a lot of them are in the parts of the system that I have glossed over. So if we go back to this slide, which has everything, some systems will often do, they'll have what they call stop words. So they'll have a set of words which are just always skipped when doing tokenization. So like the word the often will show up on a stop word list. But sometimes folks don't use stop words and they'll let it go through the whole system. But the other place where we encode knowledge about natural language is often in the result ranking. So like I totally like did not talk about how any of that works, but one of the common ranking metrics is called BM25, which comes from information retrieval, and it kind of has some nice properties in that it's like ends up being a sum of all the different words, but it penalizes words that occur in many documents, for example. So like if the word the appears in tons of documents, it won't contribute much to score, and then it will very likely get pruned out as we take the top k and for the top results. And so one of the kind of future talks in this topic is that this kind of, oh, wow, so fortuitous. What happens if a query has a really common word like the? There's 2 papers here for weekend and blockmax weekend, which are coming from the observation that if we go to the slide and if we know that the word the often has a very low score and it often gets pruned out in the top results, it's kind of wasteful for us to like generate a big set of like the top 1,000 results and or maybe potentially even more and like toss out a bunch of them, and which would be very low in relevance. So the kind of idea is like, how do we, if this is only taking the top 1,000 results, can we like push that up into the set union and say like, we're only going to keep 1,000 of them when we're taking the union of these and throwing away words like match, like our documents that match only for a word like the. Yeah.
Does the intersection algorithm generalize to sort of normal queries, not just full text queries? Like if you're doing a multi-way join over ordered indexes?
Yeah, so the question is, does the intersection algorithm generalize to regular queries or ordered indexes like B-trees and not just like this kind of compressed like integer set thing? The answer is absolutely. And it's kind of interesting, I think, how like these algorithms have different names in different fields. Like it's kind of the same thing. Actually, just on the Tiger Beetle newsletter from last week, they announced that they implemented the zigzag merge algorithm for being able to join, I think like if you have an index where it's like you have a column A and a column B and you want to answer a query like A equals 3 and B equals 4, like kind of smells like an intersection, right? And that is exactly what it's doing. And so the algorithm in that domain is called like the zigzag merge algorithm. I think it was first in Google App Engine, like in their data store in like the late 2000s. Firebase actually uses it internally. And yeah, it's pretty much the same thing of saying like, can you do the intersection of 2 sorted sets in time that is like proportional to the output size?
Cool. Thank you, Sujay.